graphing. We have to talk about graphing. So we have to do a bunch of stuff with graphing, and I'm actually going to graph 2 different functions 2 different ways each. That's a total of 4 graphs, okay? And I want to cover some of the important things and some of the common mistakes. Hopefully this will be a learning experience. Hopefully this will be a resource. Why am I still talking? Why don't I just get to it? Let's get to it. Okay, you can see I actually drew graph paper on the board because that's how much I care. And so let's just start off with this first graph. So imagine that I collect position and time data for a car rolling on a track. So I use a stopwatch, I record the position every second, and those are my positions in meters. The first thing that we want to do is to think, what do I want to plot? Well, I'm going to imagine that if it's moving at a constant velocity, I already know the model, then I can say that the velocity, and this is in the x direction, the x velocity is the change in position with respect to time. Okay, so that tells me right away something about the slope of this line. But instead, I'm going to say that I get from that, I start at t equals 0, which I do. Then I can get the following kinematic equation. X as a function of t is x0 plus v, and let's just call it v, vt, right? That's our kinematic equation, and that's really crooked, and I don't like that. It's really kind of bothering me. Let's be more level. X as a function of t is x0, the starting position, plus vt. That looks a lot better. What we want to do, if we're going to use graph paper, then we want to make a linear graph. The graph of a line looks like this. Y equals mx plus b, where that's the vertical variable, that's the horizontal variable, that's the slope, and that's the y-intercept. So if we get our function in that form, then we should have a straight line. Now in this case, you'll notice, oh, that looks like y. Oh, that looks like t. The slope would be the velocity, and x0 would be the y-intercept. So I can just plot x versus t on the horizontal axis. So let's do that. And then I'll show you some mistakes. So here's my graph paper. I'm going to reuse it. I'm going to go ahead and write my x and y labels. So I'm going to put down here t in units of seconds. And over here, I'm going to say x in units of meters. So it doesn't have to be y versus x. That's just the generic math version of a graph, of a line. The next thing I want to do is to kind of space out my values, right? So here my time's going from 0 to 4 seconds. So I could start this at 0, and then I have 1, 2, 3, 4. That's not going to be big enough. So I could go 2, I go 1, 2, 3, 4, and that's probably going to be big enough. So let's just do it that way. It's not perfect, but it's good enough. So I'm going to say this is 1, 2, 3, 4 seconds, and that would be 5, but we don't have 5 seconds. In general, if your scaling is less than half of the size of the graph, you could always expand it by 2 and to make it bigger. You do not have to start at 0, but I did because I have a 0 point over there. Now for x, I have 0.4 I'm starting at, and it goes to 1.3. So I need essentially 10 increments. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's so close. I think we can do it. So if this is 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 1.1, 1.2, and then we'll just squeeze in that other one up there. And you can't see that. There. Is that better? But I do have a label. Okay, so that's important. Now I'm going to take my data points. I'm just going to plot them one at a time. So the first one's 0 and 0.4. So it's 0 on the horizontal axis and 0.4. So it's actually right down there at the bottom. There's my point. Next one, I have 1 and 0.63. So 1, and then here's 0.6. 0.65 is right there. So it's somewhere in between there. I'm going to just kind of guess. And that's my data point. Next, I have 2 and 0.86. So 2 and then there's 0.8, and then halfway would be right there, so it's a little bit more than that. That's not the perfect one, but it's okay. It's just for fun. And then I have 3 and 1.1. So here's my 3. There's 1.1 is up here. And finally, I have 4 and 1.3. So 4, and there's 1.2. Oh, so that is 1.3 right there. So right there, it did make it. Now I have my data points. What do I do next? I need a best fit line. I need to do a linear fit. And these are all pretty good data. They could be a little bit more extreme. If I'm doing it on graph paper, I'm going to make that best fit line just with my human intuition. So I'm going to take a straight edge, and what I'm going to do is I want to line this up and see how many of these I can get close to. I want to get something that's close to as many of those as possible. I don't want to take the first one and connect dots to the second one, because that just ignores all the data points in the middle. I want a line, a straight line, that's as close to all of them as possible. It doesn't have to touch any of them. Okay, and my meter stick's not really fitting in here, so I'm just going to kind of eyeball it. Let's see, maybe like that. Okay, so I'm going to draw my best fit line. It's not perfect, okay, but you can imagine if it was on graph paper, you'd do a lot better job. So already I have some important information. It tells me that my data looks like it's in a straight line. And so that says this model that we're testing seems to be legitimate. It does say that x is proportional to t. It should be a straight line, and it looks like we have a straight line. So that's good. If I got some curve down like that, that would tell me something different, right? So maybe it's not, that function doesn't really work. But here it does work. The next important thing that I want to do is to find the slope. Because again, the slope is the change in vertical divided by the change in horizontal. That is the velocity. And you can see that down here too. If this is in the equation of a line, the slope is the term in front of the horizontal variable, which is t. So if I find the slope of this line, it should be my velocity. Let's do that. And then I'll show you the wrong things. Now, I'm going to take my graph, and I'm not drawing it too hard because I want to change this for the next example. I'm going to take my graph, and I want to find 2 points on the line that I drew. I don't want to take the 2 data points. I don't want to take any 2 data points, or again, I'm ignoring all the other data. So I want to use the line that I drew and find 2 points to calculate the slope. So I'm going to pick things that are the easiest to determine. So look right here, that one looks like it passes right through that point 1.6. So I'm going to use that one. I'm going to circle that one. It's not that data point. Now I want to find something else far away. I'm going to have to just pick this up here. And let's say that that's halfway in between. And again, it's not going to be perfect, and that's fine. So now I can calculate the slope as the change in x over the change in t. So that's going to be this x value, which is going to be equal to 1.15, minus this x value, which is, I'm sorry, yeah, that's right. The x value, which is 0.6. Now I'm going to divide by the change in time, which is 1, 2, 3, 3.5 minus 1. So that will be my velocity. Let's go ahead and plug that into your calculator. But you're going to plug it into your calculator, not my calculator. So 1.15 minus 0.6. And then 2.5 divided by that. And I get, oops, I dropped it. Okay, 1.15 enter 0.6 minus 2.5 divided by. I get 0.22. Okay, as my velocity. Let's just call it that. So notice that since my x has units of meters, my time has units of seconds, this divided by that will be meters per second. Slopes have units. Okay, so don't forget that the slope does indeed have units. What else is important? I had tangled up my cord there. Let me show you the most common mistake that I see people make with the slope. They're like, well, which slope do I use? I hear this a lot. Because I could find the slope here, I could find the slope here, I could find the slope here, they're all slopes, right? But that's not true. And in fact, if I take distance divided by time, velocity is not distance divided by time, by the way. And if I take 0.4 divided by 0, I get infinity, or undefined. So right there, that tells you that can't be true. If I take 0.63 and divide it by 1, I get 0.63. That's not the same. Because what you're really doing is finding, the slope is a rate of change, so it needs 2 data points. If I want just take that one single data point, I'm taking its x position divided by its time. It's the line from here down to the origin, which I don't have. One more thing I can get from my line is this x0, right? That's the y-intercept. So where does this intercept the y-axis? Well, here, looking at my graph right there, it's very close to 0.4, which we knew because we had it there. So we could say the initial position is 0.4. Okay, let's graph this exact same data with a computer. You should be able to do it both ways. This is the way that if you really understand what's going on, you can make a graph on graph paper. Do not make a graph on plain paper. I did it, I know, but I did it as an example. Okay. So let's switch to a graphing program. There are lots to choose from. You could use Excel, you could use Google Sheets, you could use Desmos, you could use Python. I'm going to show you how to do this with Verniers graphical analysis. It's a free program. It runs on your computer, it runs on your phone, and we use it for other things too. Oh, my computer's dying. Why is my computer dying? I don't know. Let's just plug this in right there. Okay, that's better. Okay, sorry about that. Oh, and I messed up my camera. Okay, graphical analysis. So let's switch over to the computer. Here is graphical analysis. The plain version's free, and you should use it. It's actually pretty good. So when you start up the program, it's going to say, well, what do you want to do? Do you want to collect data or not? And so I don't want to collect data. I have the data. So I'm going to click manual entry down here, manual entry. And it's going to give me just a plain data table and a graph, and there's nothing there. The first thing I want to do is to edit my graph labels. So up here, I'm going to click the X value. I want to call that time. So I'm going to change column options. I'm going to give it a name T and units of S for seconds. And then over here, I'm going to change this to X in units of meters. Now I'm going to go ahead and enter my data, which I have on my sheet over here. So I won't have to look backwards. So here's my data table. I'm going to enter these in. This one's easy, 0, 1, 2, 3, 4. And this was 0.4, 0.63, 0.86, and you have to say the numbers out loud when you enter this in. Otherwise, it doesn't work. You can try it if you want, but it doesn't really work. You have to say it. 1.1, 1.3. And you'll notice that it populated my graph already. Now, one of the things that does come up, and this happens in Sheets a lot too, and it's actually a lot easier here, is sometimes you'll get these backwards. So here I already have T on the horizontal axis and X on the vertical. If I wanted to switch those, you can click this number right here, and then I'm just going to turn off X, and then go down here and turn this one on X, and then I can put that one to T. But I don't want that. I want to go back the other way. So I'm going to turn that off, go back over here, switch this one to T, and make that one X. And there's my data. And you'll see it looks really nice. Now what I want to do is to fit a best fit line. There is a mathematical equation to find the best fit line, so we don't have to eyeball it. And the computer does that for us. So down here on this little button, graph options, I'm going to click that. And I'm going to click apply curve fit. And then I have a choice of what kind of curve. We want a linear graph. So I'm going to apply a linear graph. I'm going to click apply, and then it gives me the value. So right over here, it gives me the y-intercept, the slope of 0.227, which is pretty close to what we got, so I'm pretty happy with that. The y-intercept of 0.404, again, close to what we expected. This r value right there is a fit parameter. It's the regression coefficient. So if it was 1, that would mean it's a perfect line. It's not 1. And then the RS, don't worry about that stuff. This is just the variation between the data point and the line. There you go. The end. Now in graphical analysis, if I go over here, I can, no, not over there. I can go over to here and save the graph if I want to, or you could export it as a picture or some other option, a PDF. That's how you would save it. I don't really care. I'm not going to do that. Okay. Let's make another graph. And this one, I told you I was going to make 4 graphs. I changed my mind. I'm just going to make this one just in graphical analysis because I don't really like that graph. Okay, but if you can do it once on graph, you can do it on another graph. But I do have to explain what we're going to do in this next graph and write down the data. And then we're going to graph it and see what happens because it's a little bit different. So let's switch back to the computer. Okay. So in this experiment, this is an experiment I do in lab quite a bit. I spend a lot of time drawing that graph right there, and I feel bad erasing it, but it's erased, and you can't go back now, right? So it's gone forever. But we'll still have a video. So this experiment looks like this. So we're going to take, and if you don't understand it, it's fine. We're going to take a meter stick and balance it at the middle, and then we're going to put a mass over here as some distance away. What did I call it? I called it L. From the pivot point. And then over here, I'm going to pull down with the force F, a distance R from there. So this is a situation where if the meter stick's in equilibrium, the torque on that side is equal to the torque on this side. Technically, it would look like this. The force right here would be mg times its torque arm L, and over here, this would be F times R times sine of theta. Now, theta in this case, 90 degrees, but I just want to write it out the full way. So what we can do is to keep this whole side constant, and then I can move the location of my force that I'm pulling with and measure the distance R. So I'm going to change R and measure F. Change R, measure F, change R, measure F. Okay, and now that equation is very important. But let me write down the data. So here's the data that I got. I got R in meters. And this side stays constant. So this side, I have mgl is equal to 0.558. This is an actual experiment, 588. And this would be 88 Newton meters. Okay, so that side did not change. So this is just a constant. So here's my R, here's my F in newtons, and I get 0.1, 0.15, 0.2, 0.25, 0.3. I barely made it in there. And then the forces were 5.8, 3.9, 2.9, 2.4, 2.0. Let me go ahead and make a graph that would be very common to think of, and I'll show you what's wrong, and then we'll make a better graph. Okay, so I'm going to make this graph. I'm going to plot F versus R in graphical analysis. So I have that data right there. Let's just go back over here and make the graph. I'm going to make a new experiment. Don't save. Okay, now switch over. Again, manual entry. I'm going to call this one R in meters. I'm going to call this one F in newtons. And I'm going to enter my data. And here's my data. I have it right here. So R was 0.1, 0.15, 0.2, 0.25, 0.3. Is that right? Yep. And then my forces were 5.8, 3.9, 2.9, 2. And again, you'll notice one thing very important. I'm saying the numbers out loud. Again, like I said, if you don't say the numbers out loud, it's not going to work. You can believe me or not, but I'm just telling you it doesn't work. Okay, so right there you can see that we do not have a line, right? It's not a linear function. It's decreasing. The force is decreasing with distance. It's not even straight. It's decreasing with distance, and it's curved. So this would be a function that you couldn't really find the slope of on graph paper, so we have to do something different. I want to make a linear graph. So let's switch back to the board and figure out what we're going to do to make a graph that is indeed linear. So this is my function right here. No, wait, this is my function right here. I want it in the form of y equals mx plus b. So, but here are my two variables, f and r. If I want f on the vertical axis, let's just solve this for f. So if I solve that algebraically for f, I get f equals mgl over r sine theta. And theta is constant, and I'm just doing it for completeness. And I want to change r, but you can see that r is in the denominator. And I can't deal with that. So let me just rewrite this equation in a slightly different way. F equals mgl over sine theta, parentheses, 1 over r plus 0. Now I do have it in the form of a linear equation. If I plot y, the vertical axis is f. If I plot the horizontal axis as 1 over r, then it should be a straight line, and this should be the slope. So I'm using up here, theta is 90 degrees, so that term's 1. So my slope should be mgl. My slope should be that. Okay. So I've linearized the function. I've made it into a line by plotting f versus 1 over r. That makes it a line. F versus r is not a line. Okay. Do you see the difference? So I got this in a form that I could do that. It's possible you could do a different form, but I think this one makes the most sense. Let's do that in graphical analysis. Okay, switching back to the computer. So I have my data there. What I want to do is to add a new column where I calculate 1 over r. Now you could do this on a calculator, but you know I'm just super lazy. So I'm going to go up here and click this column and add calculated column. So to calculate stuff in graphical analysis, you need to say what are you going to call it, and then you need to tell it how to calculate it. So I'm going to call this 1 over r, and it's going to have units of 1 over meters. Now to create an expression, I can just click this insert expression, and it gives me some calculations. So I want to do 1 over r. So here, x, y, and z are column variables. A, b, and c are constants. So a over x is what I want. So I'm going to click a over x. Now I'm going to tell it, okay, what do I want for the constant a? Well, I want 1, so I'm just going to leave it like that. What do I want for the x value? I'm going to change this to r. Right there, that's it. And now it calculated that, and I have it right there. Now I can plot f versus 1 over r. That's already f. I just need to change this. Click this. I'm going to click 1 over r. And there we go. Linear function. What's next? You know what's next is to find the slope. So I'm going to add a best fit line. Click this, apply a curve fit. Linear is the automatic one that comes up. And there we go. And over here, you'll notice that my slope is 0.5701, which is pretty close to what I expected. It's not perfect. I have imperfect data, and that's fine. So I have 0.5701 newtons per 1 over meters, which is newtons per meter, which is the right units for torque. So that works. The slope here, the intercept is 0.098, which is what we would expect, right? This says that if 1 over r is, well, it doesn't really make sense too much. I'm not even going to talk about it, but it does indeed work. We did two things. We showed that our original function seems to be good because we can make it into a linear graph, and this is a line. And number two, I can find the slope, and the slope makes sense here. So there you go. Use the graphing program that you feel comfortable with. I would encourage you to find something that you like and stick with it instead of trying to use something new every time. I like graphical analysis. Here's one thing I do want to change though. Up here, graph app preferences. I go over here and then toggle light mode. I like it. I like that way better. Because then if I put it in a graph, if I put it in a document, it's not black, and I print it out, it's not going to waste all my ink. So I do that, but you do you. So that's that graphing. Hope that helps. Linear graphs, graph paper, stick to it, find the slope, don't make mistakes, and I'll talk to you later.